So this chapter dealing with free convection, we only have the budget in the semester for 2 lectures. That's it. And there's a lot of math and theory that we could spend some time on, but we just covered it last time. And today it's going to be, unfortunately, what I would call cookie cutter or follow the recipe type application-oriented approach to solving problems. So let me jump into it. Also, last time I mentioned about water and how warm water, when it's below 4 degrees C, what it'll do is it'll sink, and cooler water will float. And I kind of regretted a statement I think I made, blowing that off as being kind of a novelty, but not all that practically important. And I knew that was not right, even as I left or even as I was saying it. Lakes freeze from the top down. And if they froze from the bottom up, you could freeze a much thicker, deeper lake. And it would not be so good for anything trying to live in that lake. And so without this feature that ice floats, and when you're below 4 degrees C, that water, the warm water sinks and the cold water rises to the top, where it's then cooled the rest of the way and then freezes, then it would be a lot different world. So you could take a look at it. You remember that from high school, some class that you're in, about the importance of water freezing that way. All right. Well, we talked about setting up a coordinate system coming out from the tip. We have y, we have x going up from the tip. We talk about typically a hot surface, Ts is greater than T infinity, and gravity is acting, and the colder fluid over here will sink, the warmer fluid will rise, and so you get the development of a laminar boundary layer. And just like we had for flow over flat plate, if the plate is so long in the direction of the buoyancy-driven flow, you can get a transition between laminar and turbulent flow. And the critical Rayleigh number, based on the distance x from the sharp-edged beginning of that plate, the critical Rayleigh number is 10 to the 9, approximately. So here we go. We have a laminar turbulent criteria for flow inside a pipe. What was that value? 2,300. And it was based on the Reynolds number, based on the diameter, inner diameter. Then we had flow over a flat plate, and it was force flow. And that Reynolds number for transition from laminar to turbulent flow was 500,000. And here we have a number, it's 10 to the 9. And that's a huge number. And the Rayleigh number is not inertial to viscous forces, a ratio like that, but it's just like the Reynolds number, but it's buoyancy to viscous. So the Rayleigh number is what drives the natural convection. So there's another critical number by which you distinguish the transition from laminar to turbulent. There's a lot of correlations. What you do is you find the recommended correlation. If you pick up a different textbook, maybe somebody recommended a different correlation, because a lot of people have published correlations. This would flow over a hot plate in a cool fluid, or here, cool fluid or cool plate in a warm fluid. It would fall. The boundary layer would fall. If it has an angle, you modify G in that Rayleigh number. The Rayleigh number is G beta delta T L cubed over nu alpha, and you would put in here a cosine of the angle theta, modify that G if it's slightly tilted up to 60 degrees, it'll work. Use the same equation, just modify G in the Rayleigh number. Here's other correlations. What you do is you say, okay, what is it? Is it the upper surface of a hot plate or the lower surface of a cold plate? And then you check the Rayleigh number and the Prandtl number, restrictions on the correlation, and plug and chug. All right. We have an oven door, and they give us the height, h, in the gravitational field. So this is 0.6 meters plus the width. which is 0.8 meters. It has an average surface temperature, so you have the temperature of the surface of 36 degrees C. A lot of times, just go ahead and convert 36 to 9 Kelvin. And then the temperature or the fluid far away in the room is 23 degrees C. It's 296 degrees, well, just Kelvin, degrees C and Kelvin. Yeah. All right. Estimate the heat loss into the room by free convection. I know it's not a sharp edged plate at the bottom, but use that correlation because that's the best correlation we have. So we'd want to use this correlation right here. And so the game is to, if I'm looking to get the heat loss, then I'm calculating Q. I'll have HA delta T. I got the A, I got the delta T, I need the H. How do I get the H? H is embedded in the definition of Nusselt number. H, it's on a, L is the length scale, L right here. And so to be consistent, it's like the height in the direction of gravity is our length scale to be used. So it's HL over K of the fluid. So to find H, you unravel the Nusselt number. That's what I say, unravel it. And how do I get the Nusselt number? Use the correlation. That would be the correlation to use. So to use the correlation, I need the Rayleigh number based on that length scale. Just repeating, G beta delta T L cubed divided by nu alpha. Which properties are very temperature dependent? Well, I need to get beta. Isn't beta equal to 1 over T? But which T? T of the surface, T infinity of the fluid, which T? Film temperature, exactly. And so you calculate the film temperature, which is just Ts plus T infinity divided by 2. The film temperature, 302.5 Kelvin. Not nice. You have to interpolate to get your properties because we want to get, well, beta is just 1 over 302.5 Kelvin, but the nu and the alpha are harder to get. So nu, when I did the interpolation, was 1.6 times 10 to the minus 5 meters squared per second, and alpha is 2.28 times 10 to the minus 5 meters squared per alpha. So nu and alpha are temperature dependent, and beta definitely is temperature dependent. And so what I calculated for the Rayleigh number is 2.47 times 10 to the 8th. I take a look. This correlation's a wide range of Rayleigh number, and it fits. I didn't copy the restriction or discussion of the restriction. The Prandtl number is very slightly temperature dependent, 0.71. And then we can calculate the Nusselt number. The Nusselt number, using that correlation, came in at 80.13. Are there dimensions on the Nusselt number? Dimensionless. Perfect. Dimensionless. And then we calculate the H, which is 3.54 watts per meter squared Kelvin. That's really low. If I was doing this calculation, I'd probably boost it to at least 5 because this just seems too low. First of all, it's pretty hard to have an oven door in a kitchen that's really still. There's nobody walking through it. There's no fan, no motion. And a little bit of motion will promote that heat transfer and lead to a larger H. But anyway, 3.54 is the value we calculate. Hence, you can get the Q. The Q comes in at 22.1 watts. Part B says the thermal radiation, assuming the door has an emissivity of 1. Well, we go back to Chapter 1. Q, we'll call this convection. Q radiation is just going to be the emissivity of the surface that's radiating out into a large room. It will have the Stefan-Boltzmann constant. We'll have the area. We'll have the temperature of the surface to the 4th power, and then the temperature of the room or the surroundings to the 4th power. So we have all of these. The Stefan-Boltzmann constant, 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. And when I calculated Q, I don't know where to put it. Maybe I'll try and squeeze it right in here. Q, this is radiation, RAD. It comes in at 39.2 watts per just watts. So it's almost double what the convection is. And so often when you're studying natural convection in air, and you do have warm surfaces, you should account for thermal radiation as well. So if both of those would be occurring at the same time, the total heat removal from the oven door would be 61.3 watts. And looking back at it, this would account for about 36%, a little over a third, and this would be the 64% for the radiation. All right, so we also have off of a horizontal cylinder a long correlation. When you see a correlation like this, it's empirical fit. And as well as off of a sphere, it's a lot of empirical fit to the correlation. All right. I mentioned this, I believe that the details are quite complex about the thickness of the boundary layer and how it actually grows, and the local Nusselt number is a function of the angle going around. Between 0 and 90 degrees, that Nusselt number is pretty flat, but then because of the thickness of the boundary layer getting larger, the local Nusselt number drops off as it gets closer to 180 degrees. That's all too much. So we often just look and calculate an average Nusselt number over a wide range of Rayleigh numbers, or we just piecemeal it with a very simple expression. What happens if you have a long vertical cylinder? Well, you can look for a correlation of a long vertical cylinder, but as an engineer you cut it and stretch it out, and so this width would be pi times diameter, or 2 pi r, wouldn't it? And then the height, or L, would be given like that. And so if you wanted to calculate natural convection off of it needs to be a relatively large diameter cylinder. The book has the criteria for how large it needs to be. But we often use this. We just would conceptually treat it as a large plate. Well, let's take a look again at this sphere equation, and there's this interesting factor of 2 sitting out there. And if you plot the Nusselt number, the average Nusselt number, as a function of the Rayleigh number, for low Rayleigh number, guess what? This part of the contribution is much smaller than 2, and so it's flat. But then finally this part will grow, because you can see it's a function of Rayleigh number, it's going to get larger, and it'll have a transition that'll go a straight line like this on a log-log plot, where the slope of this line on a log-log plot is 1/4 because of the exponent right here on that Rayleigh number. So for large Rayleigh number, you could neglect the 2. For low Rayleigh number, you could neglect the function of Rayleigh number. It's just constant. The Nusselt number is just a constant. And somebody says, how does that come about? Well, when you have very low Rayleigh number, what is that? It's very still fluid. The fluid's not moving. There's negligible buoyancy effect. We already studied when you have a sphere, remember this is just for a sphere, of radius r, let's call it r1, and you insulate it and you put around it a layer of stagnant insulation of radius r2. Do you remember something like that, where we said the rate of heat transfer going through that layer of insulation, that Q, is equal to the delta T divided by the resistance. Let me write it like this. Delta T, T1 minus T2 is the delta T, divided by the resistance. It's 1 over the R1 minus 1 over R2 divided by 4 pi k. That was our resistance for a layer of insulation going from radius 1 to radius 2 around the sphere. Look familiar? Well, let me just rewrite it like this. 4 pi k delta t. And what I'm going to do conceptually is we're going to let R2 continue to get larger and larger and larger. And then what happens to, it just becomes 1 over R1, doesn't it? Because 1 over R2, if R2 gets larger, 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 what does that do? That's negligible. So we subtract 0. So what you have is if you have a model for the heat transfer off of a hot sphere into a cool fluid where the fluid far away is at temperature T2. Well, somebody says, you know what, that's our conduction in a quiescent fluid. What was our model for convection? Our model for convection is equal to the model of conduction. The convection model, though, is an HA delta T, true? What is the area of a sphere of radius r? What is it? 4 pi r squared times delta t. So that's equal to 4 pi k r delta t. The delta t's are on both sides. The 4 pi's are on both sides. Get rid of one of the r's. And what do we have? We have h times r, and I can bring over that k is equal to 1. This looks like a Nusselt number, doesn't it? But that Nusselt number has a length scale of r. And what is our length scale of this Nusselt number? D. So if I wanted to, I would multiply this by 2, multiply by 2. Now 2 times r is d, so we have hd divided by k, so there's my Nusselt number based on 2. And there's a quick derivation of that 2. Where did that 2 come from? You can actually derive it. It's one of these. In a chapter full of empirical correlations and curve fits, the 2 can be explained, which is kind of nice. So the 2 comes from just stagnant conduction. Somebody says, why don't we go to our correlation for a long, infinitely long horizontal cylinder and see if we can do the same thing? You can try it, it won't work. There's something about the geometry around the sphere it works, and for a cylinder it doesn't work. Okay, time permitting, we'll solve another problem. So here we have a vertical double pane window having a height of 1.5 meter and a width of 1.5 meter and a 20 millimeter gap. And I forgot to change this problem, so I'm going to change it right now. The height is 0.6 and the width is 0.6 and the gap is 20 millimeters. Okay. It's filled with atmospheric air inside between the 2 panes, and it separates quiescent room air that's at 25 degrees C on one side from quiescent outdoor air at negative 10 degrees C on the other side. So here's our 2 panes of glass, and we have the air over here. It's on the inside is 25, and the air over here is negative 10 degrees C. Neglect thermal radiation exchange between the window panes as well as between each pane and its surroundings. So only convection is considered. Also neglect thermal resistance within each pane, meaning you could have a slightly different temperature, the left side, the right side of each of those window panes, but if it's negligible thermal resistance, you just talk about one temperature of the glass, that window pane, and one temperature there. So we have 4 temperatures that are unique. The temperature of the air on the inside, the temperature of the air on the outside, the pane window on the inside, and then the pane temperature on the outside. Estimate the heat loss from the room to the outside So what we have is we have a resistance to heat transfer, a resistance to heat transfer, and a resistance to heat transfer. We would solve the 1 over h on the inside area and 1 over h on the outside area using the Rayleigh number and the Nusselt number correlation, just like what we did for the previous problem, vertical surface. Even though it's not a knife-edge sharp plate in a large room, it's what the best we have. But here, what do we have to do? We have to look for the right correlation, which is describing air that's trapped in a kind of a slender rectangular enclosure. And people have studied that. And so it's a rectangular cavity. You have the thickness of the cavity, L. And that L, for our problem, is 20 millimeters, 0.020 meters. Its height was 0.6 meters. Its width was 0.6 meters. And somebody studied this problem and they curve fit the data and they have a coefficient, the Rayleigh number to a 4th power, Prandtl number to a very small exponent, and then a height to length ratio to the negative 0.3. So it's really for slender cavities, tall, slender cavities, where this height to length ratio is between 10 and 40, etc. So what we do is we check our height to length ratio for this problem, and it comes right in at 30. We see that it falls in the range. That's good. What's our Prandtl number for air? It's about 0.7. We look at this, 1 to 2 times 10 to the 4. It's slightly outside the range, but I don't have anything better. I'm going to use it. Okay? And then the Rayleigh number, well, let's compute the Rayleigh number, but let's jump back here. I'm going to use this correlation in a minute, but I need to go back here and say we're going to get a convection coefficient between the panes in that gap region. This is a gap region, and then we'll have an area. Why don't we have 2 convection coefficients to move it from the pane into the air and then from the air to the next pane? Well, the engineers that developed these correlations said we're just going to have one convection coefficient that moves from one solid surface into the fluid all the way to the other solid surface. So that may be a conceptual sticking point when you first read it, right? So it's 1 over HA to go from the solid temperatures, nodes. Okay, so here we have to get our film temperature to calculate properties like nu and alpha and Prandtl number. For not only the inside, we need the film temperature for the outside. Nu, alpha, Prandtl number are the ones that are very temperature dependent or more temperature dependent than others. And this film temperature here, well, are those the same film temperature? No. But how do I solve for the film temperature? Well, if I knew the pane temperatures, then it's like I already have solved for the problem. It's back to my analogy with the merry-go-round. You just have to jump in there somehow, one shape or form. So what I would do is I would say I'm going to assume some of the pane temperatures. I'm going to actually calculate the film temperatures, get the fluid properties, use the correlations, get the H's, solve for the updated temperatures, and if I feel like it or I have time, update the estimate to the film temperatures. So I look at it, and it's from 25 to negative 10. That's 35 degree delta T total. I'm going to say it's about 10 degree delta T here, about 10 degree delta T there. That leaves a 15 degree delta T there. So I'm going to guess that this temperature of pane 1 starts at, for my guess, would be 15 degrees, and this would be at 0 degrees. That allows me then to get the film temperature. It would be 20 degrees C here. What would it be here? 7.5 degrees C. And here it would be negative 5 degrees C. Then I can get the properties, get the Rayleigh number, get the Nusselt number, get the H's. When I did that, I calculated the H on the inside to come in at a low value 3.31. How about the H in the gap? The H in the gap came in at 2.09, and the H on the outside came in at 3.44. It's essentially the same. Look at how close those numbers are. The convection on the inside and outside. What's really different, what's driving it is the temperature-dependent properties, slightly different values. So the overall resistance was 45% of the overall resistance due to the gap, and right at 28% and 27% contribute the other two components for the resistance to the heat transfer. Well, when I iterated once or twice, the temperature of pane 1 for a final value came in at 15.1 degrees C, and the temperature of pane 2 came in at negative 0.5 degrees C. Not much. I'm just showing you that, yes, you have to iterate if you really want it to converge. And then the Q, the overall Q, comes in at 11.8 watts. Let me ask a question. Clicker question, or first clicker question. If you have forced convection on the outside, so the wind is blowing on the outside. Instead of being a calm day outside, the wind is now blowing over the window. We have a double pane window. That's what we're analyzing. What happens to Q? It was 11.8. Does it go up, stay the same, or go down? Answer A, B, or C. What does Q do if you have forced convection on the outside? So this goes up, stays the same, and goes down. A, B, or C? All right, everybody in? Let me ask another question. If you have forced convection, if air blows harder on the outside, right? What does H on the outside do? Oh, it used to be 3.4 watts per meter squared degree C, right? What is H on the outside going to do? Is it going to go up? Answer A. Stay the same, unchanged? Answer B. Or go down? Answer C. What does the convection coefficient do? H on the outside. If you start to have a windy day instead of a calm day. All right. So when do we have a low H? Just as not a clicker question. When do you have a low H? Think about boundary layers. Do you have a thick boundary layer or a thin boundary layer for a low H? Low convection coefficient. You have thick boundary layer, right? And so what happens when you start ripping fluid across the surface? You start thinning out that boundary layer. Maybe it becomes turbulent, really rips it up and chews it up and makes a very thin boundary layer. That's going to promote the convection coefficient. H is going to go up as I really blow the air across it. So the best answer, isn't it, for question 2, was that the convection coefficient goes up if air is being forced or it blows, it's windy outside. All right. And then this one. So if I have a higher H on the outside because the wind is blowing, it's going to have a larger Q. The rate of heat transfer, Q, goes up. Make sense? Very good. All right. And then when I go back and solve, I already did that, solve for the temperature panes. You really have to do that, iterate back and forth to solve this problem. Let's talk about heat transfer and natural convection in the annular space. So think about long, thin-walled concentric tubes. So here's the inner tube, here's the outer tube, and they're very long. They go way back like that. All right. And the The space, the annular space between them is filled with air and at atmospheric pressure. The inner tube has an inner diameter. D on the inside is 0.10 meter, so 10 centimeters, and a temperature on the inside of 80 degrees C. And the diameter on the outside is a 0.20 meter. So, and the temperature of the surface is 25 degrees C there. Neglecting thermal radiation, estimate the convection heat loss per meter of tube length across the airspace. So what symbol would you suggest we use for the answer? It's heat loss per meter of tube length. Q prime or Q over L? Q prime or Q over L? What would be the SI units of my answer? Watts per meter. Watts per meter. Very good. So now what would be the approach? Well, we're going to basically have to figure out how to treat the air would normally be stagnant in between. True? But because of the hot surface and the cool, it would promote the heat transfer. It'd be more heat transfer from the inner hot to the cooler outer surface. Well, you look through the textbook and you say, oh, you know what? There's some empirical correlations for enclosures and between concentric cylinders, and you just like we did before, and you find that somebody studied this and they've reported a correlation. So we have a flow pattern. It looks like you might suspect it's symmetrical about the center here, and it's coming up and around and down, and there's a flow pattern. And they said what we'd like to do to predict the Q is to use an effective conductivity. If you were the first to do it, I think most of us would like to do that. We would like to approach it that way. So we have the effective conductivity divided by the thermal conductivity of the stagnant fluid. That'll give us some ratio. Maybe this is 2, meaning, oh, it's as if the conductivity has been doubled. That's the effect of the convection. Or maybe it's 4, maybe it's 6, whatever this ratio is. Well, how do I get it? Well, somebody's curve fit to experimental data. What's going to drive it is some Rayleigh number. But the Rayleigh number for this, I need some length scale. What would be an appropriate length scale? Well, somebody studied it and they said, let's use this characteristic length scale, which is based on the inner and outer radius. So you have the equation now. Look at that equation. It doesn't look very appealing to me analytically. But somebody's reported this is a good way to fit the data. I've tried a number of algorithms, and this is a good way to fit it. So for this problem, you go and we were given the radius, and so you calculate the characteristic length. It comes in at 0.026365 meter. A lot of digits, but it's an intermediate calculation. And then I have to get that Rayleigh number. The Rayleigh number uses that characteristic length, but it's G, we know that one. It's beta, I need 1 over the film temperature. The delta T, the inner and outer temperatures, that was given. And then we have this characteristic length cubed, we just calculated that, over nu alpha. So we calculate the film temperature, and then we calculate the properties at that film temperature. It's around 325.5 Kelvin for the film. You get properties. You calculate that Rayleigh number. The Rayleigh number comes in at 6.34 times 10 to the 4th. And then you shove it into this correlation with a Prandtl number of about 0.71. 0.71 Prandtl number. You get good at your calculator, please. We're beyond messing up on calculators at this point in your career, right? Please get really good at your calculators. And I found that this ratio of K effective over K for this problem comes in a little over 5. Meaning it's as if that motion from buoyancy would almost be a factor of 5 times the stagnant gas conductivity. So you, instead of putting in a K of the stagnant gas of 0.028 watts per meter degree C. Put in effective conductivity 5 times that. It's like 14 point something. I calculated 14.1 watts per meter degree C. And then we could calculate the Q for this problem. I brought that L over, so Q divided by L, and you put the 2 pi, etc., and you get that the Q over L is 70.6 watts per meter. Thank you for your attention. Sorry I had to rush. We'll see you next time.